Hello, I'm Kashif. I welcome you to my YouTube channel on statistics. First of all, thank you so much for viewing this video, for being with me. I'm very grateful to you, and I hope that you would be able to learn for what you are here. I would highly recommend you to watch the full video to understand the concept. And if you don't like any part of this video, please write in the comment section what part or what you did not like, and I would try to improve. I would try to come up with more quality videos, or if I learn my mistakes. With this note, I would like to remind you another point that this is the continuation of my first video. So I highly recommend you to please watch the first video on sampling distribution. And in fact, this is a series of lectures. So you want to really get the whole message of statistics through me, then please watch the videos from number 1, 2, 3, and this is the fourth in series. So you would be able to actually understand what we are discussing here and what are the hypotheses that I have taken, because as I have a couple of times announced that statistics must be learned when the series of lectures should be followed, instead of picking up for one topic or another topic from different platforms like YouTube and other internet, Google search. Having said that, let me just get back to my topic of today, which is sampling distribution. In the previous video, we were discussing about the probability distribution, and I discussed about what is sampling distribution, and I told you that sampling distribution is basically a probability distribution of statistic, of statistics, basically the characteristics we can say, and that characteristics refers to mu, refers to mean, refers to standard deviation. Okay, in this video actually we will just continue. So what we were doing, we learned about how when it comes to actually select the sample, we can actually types of sampling designs, we call it, or sampling techniques we call. So if you say design, or what sometimes we call it techniques, actually we can see random sampling, stratified sampling. I will make a particular video on types of samples, type of sampling techniques, but these two techniques, particularly stratified and random sampling, are important to discuss now before I move on to my probability distribution of sampling. So stratified sampling, stratified sampling and random sampling. So random sampling, by name itself, you can understand that refers to the random selection of your element, or of your any item, your any object. So randomly you do, which means that all objects have equal chances to be, selected by the researcher, by the one who is actually performing a study from the population actually. And as I said in my previous video, I'm assuming that population is actually unknown to us, and because population could be unknown as well, right? So random sampling, as I said, refers to, and when we have random sampling, it basically refers to unbiased sampling, that all elements have equal chances, and that becomes unbiased. So there's nothing like favoritism, or one element has more chances, over other elements. So this is the benefit. But we have another, but random sampling is possible only when I can write here random sampling is possible. Basically, random sampling is possible only when attributes or the characteristics of objects, of elements, are homogeneous. They have the same size, all the attributes, there could be millions of attributes, they should be the same. Then only your because what we are telling, from the first video I'm discussing, that your mean should be equivalent to, or we are trying to make it equivalent to, the population mean. And when it is not equivalent, it leads to an error, and that error is called sampling error, that I discussed in my previous video, in video number 1 on sampling distribution, video number 3 in the series actually. So Random sampling, as I have said, all objects, I would say all objects have, okay, have equal chances to be selected. Okay, so how this random sampling could be justified? When I am writing here, uh, let me just write that they are homogeneous. They are homogeneous. That they have same color or size or shapes or whatever the attributes are there. So whatever you select will actually represent exactly the other. But we have on the other hand, we have other sampling technique called stratified. Let me write stratified sampling. What does it is again, stratified. We call it sometimes stratified random sampling, but this is not homogeneous. This is actually heterogeneous. What does it mean? That uh, in, let's say, here's the population. Okay, so this is our different, this is our different samples, this is our different sample, but they belong to the same population, but some of them, for example, they have equivalent features, but both of them actually are different from this one. Okay, so I would say the 1 2 3, so I can say that 1 and 2 are very much similar, but they are different from the 1 and 3, sorry, are very much similar, but they are different from 2. Okay, so but they belong to the same population. They belong to the same population. However, they are differ actually in attribute, and that's why. So what we do, we define our technique, and so that if we define them and we choose the selection by heterogeneous random sampling, then it can help us to reduce the sampling error, because we are already aware that our sample actually may not represent or may help us inferring the population mean actually. Okay, so I will make a separate video, okay, in the end, so that it would be more clear that maybe we can take some examples from and other multi-stage sampling and other types of samplings techniques are there. So we can, but yes, for this, we have to understand heterogeneous characteristics of stratified sampling and homogeneous, which is basically a characteristic of random sampling. Having said that, now our next point is, why do we do sampling actually? Why do we do sampling? And if you remember, I told you in my previous class that if you want to reduce the sampling error, okay, that your mean may not be equivalent to the mu, and that's because of error, and that is called sampling error. How we can reduce that? Okay, how we can actually reduce this error, and this can be done by selecting a sample, by applying some techniques, by giving training to a researcher. A couple of things could be done. By it also depends on the experience of a researcher, that how he actually selects the data. And there are so many institutions across the world who are specialized in collecting data actually, and just collecting data, because this is the first step. And selection is actually, everything depends on the selection, that which data you are going to select actually. So having said that, now the task is how you can reduce the sampling error. So what we do, we take a sample from a population. Now how we select it, as I said, it matters. So when it comes to the selection, so let me write down first of all, why do we, so select the sample, let's say. So I can write, we collect samples. Okay, we collect sample. Okay, we collect sample. So why we collect samples? For knowing different means. Yeah, we different means x bar, because from the sample. So uh, and as many samples as possible, because there is a theory called central limit theorem, which I will be discussing in future, that says that the more big sample you have, bigger sample you have, the more chances of getting closer to the mu is. So, and that theory says n should be equivalent to 30 number of, that we will be discussing before we actually move on to normal distribution. Okay, so because this video otherwise would be very long, please keep watching all my entire series to understand all these concepts. Having said that, so what we're discussing, that different means, and try to see from where to where the values, I would try and say the values, sorry, values are varying, varying, varying. So why do we take so many samples? So let's take one sample and take the mean, take from the same population, take another sample, okay, and find out the mean, take maybe 3 4 samples, we do sampling, and try to know that, and the means actually, and see the average mean, then see the average mean, and then see the frequency of that mean, and that frequency would be equivalent to the population mean, and how it looks like. Okay, you have a confusion, don't worry, I'm going to address that now. When it comes to selection of sample, as I have already discussed, that we use normally two methods, that is called with replacement, with replacement, and without replacement, with replacement and without replacement. And that I discussed in my previous class is a topic of probability. To make sure to understand it completely, please watch my previous video. Okay, I have given link in the description below. So the same in my previous class, I took as population 2, 4, 6, 8, 10. Okay, and then I told you that when it comes to the selection, first you should decide that which sampling technique you are going to use, stratified or random sampling or multi-stage sampling. Okay, different techniques we have. And then while doing that, while keeping in your mind that which technique you are following, then you should do that it is going to be with replacement or without replacement. Now, what is the main difference? I have already discussed, now, let's say if this is a with replacement, okay, which means that you take an object, let's say my sample size is n is equal to, my sample size is 2, okay, and we are doing with replacement. In this video, I would be covering only with replacement because otherwise video would be very long. But in my very next video, I'm going to discuss without replacement. Okay, having said that, 2, 4, 6, 8, 10 is our population, n is equal to 2, which means our sample size, and this is my population, this is my big N, this is my small n, and I'm saying with replacement. Okay, with replacement, right? And now you may say, so how about this? No, only n is equal to 2. Why not n is equal to 3? Maybe we can choose yes. It could be n could be 3, 4, blah blah blah, and it could be n number of observations. So it really, sorry, it really does not matter. But when we do the sampling, actually, we have different formulas of, or we can say techniques, when n size is 2, sample size is 2, has a different technique. When we have n 3 or more than 3, we have a different technique. Okay, that I'm going to discuss with you. Okay, so I'm assuming that this is random sampling, not stratified, random sampling technique we are following. Okay, and we are going to do n is equal to 2. We have n, this one, and sample size is 2. Okay, having said that, so first of all, what I said, that we take this so many, we try to know so many means of different samples, to know what is the actually the average, what the frequency, in frequency, which mean is higher, so that we can say that the probability of our population mean and the sample mean is very close to each other when we know the population. Okay, now let's do this. Now I'm assuming a question here. I'm assuming a question here that whenever you are doing, with replacement, first of all, you should try to know that how many samples could be possible, okay, from one population. How many samples could be possible? So there is a formula. There is a formula of called, here I can write down n to power n actually. Okay, what does it mean? That there I have how many objects? 1, 2, 3, 4, 5 objects. How many sample size? 2. It means 25 samples are possible. 25 samples are possible. Okay, so it will take long time. So to make it short, okay, now I'm just taking my another x. Let's say my x is just 2, 4, 6. Okay, my x is, and my n is 2. This is my big N. So how many size are possible now? N is equal to, n is 3 because 1, 2, 3, 3, and n is 2, here 2. So 3 multiplied by 3 is equal to 9. So 9 possible samples. What does it mean? Okay, so from one population, we can make actually 9 samples, okay, when we have sample size actually 2, okay, and the population size is given as and again and again, I'm emphasizing on that, that population is given here. What population is, what is sample? Please watch my first video. It will be very clear. Okay, 3 3 is 9, so 9 samples very quickly. Now I have to make actually the 9 samples, possible samples. So how we can actually do this? Let's have a look. Now here you put the values because we have, yeah, here we have, let me change the color. So here we have 2, 4, 6. So 2, 4, 6, 2, 4, 6, 2, 4, 6. And very quickly we make now, we do the samples. So 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, yeah, 6, 2, 6, 4, 6, 6. Okay, now let's find out the mean of these 9. So we have 9, 1, 3, 3, 6, 3, 9. Yeah, so now let's do the mean of 9 samples. Yeah, okay, so here the first is this one, the first is this one, 2 plus 2, 2 plus 2 divided by 2 is going to be 2, 2 plus 4, 2 plus 2 4, and 2, right? Likewise 3, 4 plus 2 6, plus 6 plus 2 divided by 4, 4, sorry, not 8, and likewise 3, 4, 5, 6 plus 4 10, 5 is 10, 8, 2 4 is 8, 4 plus 6 10. No, here I should put here, this is by mistake. Okay, 4 and 10, 5, and 6 plus 2, 6 is 12. So possible samples mean how many possible? So this is what I said. Do you remember my definition here? What I said? We collect sample for knowing different means. This is what I was referring to, that how to collect different means and try to see from where to where the values are varying. You get my point? So here, by doing this sampling, I have come to know that there are actually 9 sample means, okay, from the same population. Look, it depends on the, as I have said that. And now we would see that, but is it really equivalent to the population mu or not? Just keep watching my video till the end and you would understand. Okay, now look at this one. So how we say, let's do this way. This is another technique. Okay, okay, so here, always write down the frequency of frequency of means actually. Okay, and here we write range of observations. Okay, or items or elements of population, observation of populations we sometimes write, or even we can say, you know, um, the means as well. I'll show you how. For example, so 1, 2, 3, which means frequency, how often they are actually, occurring. So let's say here range means my mean starting from 2 to 6. So we can do like this, 2, and we can say 3, 4, 5, 6. Okay, this is what I said, range. Okay, now so 2 appears how many times? Just one. Okay, because it's once. Now 3 appears how many times? 3 times, 2 times. So 3. And 4 appears how many times? You can see 3 times. And 5 appears how many times? Again 2 times. 2 times. So here, and 6 appear once. So here you can see I'm talking about the frequency. Yeah, the frequency. Okay, so okay, let me draw again. And now, and that's, if we draw the chart, this chart will draw something like that. This will actually touch this part as well. Okay, so now when you make it on computer, it will actually touch, and it looks exactly like, and that is, now I will come to that point. But now here, now check whether our sample mean is equivalent to the population mean, my theory, the theory that mean is equal to my mu, or let me do this way, is really equivalent to or not. Okay, let's check. What is the mean? Highest frequency. So here there is a normal what you call assumption that here your mean, your median, and your mode both all are equal to each other. And here you can see that mean actually it is 4, and median and 4 is also mode, because mode is highest in frequency, so 3 times. And also this is median, equally divided, you can see. Yeah, so here it's proven that. Now let's check what was the mu actually. So here mu is, what is mu? 2 plus 4 plus 6. I'm trying to know mu. So mu is 2 plus 4 plus 6 is equal to 6 plus 4, 10 plus 12, 12 divided by 3. So actually our mu is 4, and you can see from here our mean is also 4. So here 4 is actually 4. Yeah, so mean is actually equivalent to the median. Okay, having said that, so this is how. And guys, one more point, and that this curve is, this distribution is called normal distribution. Normal distribution, which means that when your mean value, when your sample mean value is actually equivalent to the population mean or very close to that. Okay, we have separate chapter on normal distribution curve, but if you keep this curve in your mind, because all hypothesis testing, it is t-test or any test, z-test, any test, you are going to ANOVA test, all the tests, you can actually learn if you know the quickly, if you know the concept of normal distribution curve. Okay, very quickly. So this is what n is equal to 2, sample size 2. So now you understand the definition. We collect samples. Okay, I would write samples, sorry, for knowing different means and try to see from where to where the values are varying. So from where to where the values are varying from 2 to actually 6. Yeah, okay. 2 to 6, and in terms of means actually, because we have actually 2 appears once, and then 3 appears twice, and then thrice, like that. Okay, so now n is 3. When our n is 3, n is 3 or more, I will not take more, otherwise the subject would be too long. Let's take the same question. Okay, and this is sample size 3. Sorry, x is, what was the x in previous case? Yeah, 2, 4, 6. The same question, but n is 3. Okay, and it, by the way guys, it could be 2, 4, 6, 8, 10, and in millions. It does not matter. Just because I don't want this video to be very long, I'm just taking small population and sample. Okay, having said that, so first of all, the first thing first, that you try to know your how many sample could be possible actually. So n, sorry, so n, this time n, this is basically n to power n. So let me write down. So n is 3. This is our n. So 3, and this is also 3. So this is going to be 3 multiplied by 3. Again, 9 samples. Okay, 9 samples. But the same question, if there would be, let's say, x would be like this: 2, 4, 6, 8, 10. So then what would happen? Then n is 5, and then sample size is 3. So it would be 5 multiplied by 5. This could be 125. And so cover of 125 is different. And that's why, and in these cases, uh, it is recommended to use the softwares. Okay. Anyways, let's see how we can do actually when there are 27. So there are 9 samples. There could be many as possible. If it would be, let's say, n would be 4, then it would be, let's say, n would be 4, then it would be 4 multiplied by 4 multiplied by 4, it would be 64. Okay, likewise, so many things are possible. Okay, now when we have n more than 2, which is 3 or more than 3, then we have a technique. Okay, what technique is this? Look at here. Now, how many samples are possible? These are possible samples, right? Write it here. What is the actually n size, big N size? That is 3. Big N size always, yeah? 3. 3 3s are 9, 3 3 1. So now we have, just I am highlighting it because I need these two values. Now come to this and make the sample. Okay, first 3, what does it mean? It means that you have to write, okay, each digit, each sample observation, sorry, population observation 3 times. So 2, 3 times, 1, 2, 3. Then 4, 3 times, 4, 4, 4. Then 6, is it 6? Yeah, 6, 3 times, 1, 2, 3. Okay, now next is 1. So what is 1? That each digit has to be written 1. So 2, 4, 6, 2, 4, 6, 2, 4, 6, and that's all. And then now what we do, let's make possible samples. Let me make a small space here so that I don't need to actually write below. So here these are the mean, or I would say here possible samples or sample means. Yeah, possible sample means. Okay, now 2 plus 2 divided by 2, here 4 divided by 2, 2, 3, 4, 6, it is 6. So 3, 4, 10, 5, 4, I hope they are correct. 6 plus 4, 10. I hope I'm not making any mistake because I'm doing very quickly. 6 plus 6, 12. Okay, so I think 2, 6, 4, 10, and this is actually 5, 5, and then 6 plus 2, this is 6 actually. Yeah, and then again do the same job, like right here the frequency, here the range. So 1, 2, 3, this is my frequency. Okay, okay, now the range is actually, we can write down the range: 2, 3, 4, 5, 6, right? Okay, so 2 appears how many times? Just once. Okay, once. 3 appears how many times? 1, 2. Okay, 2. 3 4 appears how many times? 1, 2, 3. Okay, 5 appears how many times? 1, 2. It should be like this little bit, yeah, because this is 2, so it should be now. And 6 appears how many times? Just 2. And then you make the, and then you see again. So again, actually the mean is equal to the mu. But folks, you have to remember, you have to understand, not every time this curve is going to be looking like bell-shaped curve. Okay, not every time. And that's what we have to discuss in our upcoming videos. Okay, in today's video, I covered about when sample size is two or more than two, okay, and with replacement, okay. If you want to learn about how when we do without replacement, then we have a different technique altogether. We use permutation combination methods that I would be discussing in my next video. So I would request you to please continue to watch my entire series. And if you have any doubt or any point, please write in the comment section. And I recommend you again that please watch all my previous videos to understand all these concepts. Okay, so if you do not understand this how to prepare these, because after that, after some time, you will just preparing these graphs, so one should know that what does this graph mean actually, that what it does refer to. Okay, and that's called normal distribution. But it's not necessary that charts could be sometime like this, charts could be sometime like this. And then how we can, and if the chart is like this, it means that my mean is not equivalent to the mu. Okay, and then how we make our mean equivalent to the mu? If population is given, that we can do by using some techniques. Okay, but when the population is unknown, when it is we don't know, then how can we do that? These are the things that I will continue to discuss with you. And we will be touching every single basic thing. So thank you so much. If I hope you like this video and you understand for what actually you viewed my video. If you want to, if you have some suggestion, please suggest me. I will try to improve the quality. Thank you so much and see you in next video. Bye bye. Take care.